Okay. What we're going to go on to look at now is combining the two forces. So when we combine the chemical and electrical, we're basically putting the two forces that are acting on the particles together. And while we speak about them as separate forces, in actuality, right, in physiology, your body doesn't separate these forces. It's one force. They are caused by different factors. That's why we separate them out to describe them further. But in actuality, it's the electrochemical driving force together, compounded, they're going to be acting on any one particle. So it's the sum of these two forces that are acting on a particle. And so let's take a cation like potassium, for example. We can break out the concentration gradient and look at the difference in the number of particles, which is the chemical driving force. So higher concentration on the inside for potassium, lower concentration on the outside for potassium. So there's a chemical force wanting to move it out. And then if we took the electrical driving force under consideration, that is based upon the charge. So potassium is positively charged and the polarity of the cell. There's an overwhelming negative charge on the inside, overwhelming positive charge on the outside. So a cation like potassium wants to move on the inside of the cell. So we can already see that if we were looking at these two forces separately, the particle would move in two different directions. In actuality, we know that that's not true. We know that what we have to do is combine the two forces, literally add them together, and then we're going to try to determine what is the overall direction that both of these forces acting on potassium would actually move potassium. In other words, if both of these forces exist, in what direction will potassium actually move in? Okay, and that's what we're going to go on to describe. How do we determine the direction of the electrochemical driving force, even when the forces are acting in opposite directions? Okay, so if the chemical and electrical forces act in the same direction, this is pretty easy, right? We simply add those two values together. We add the sum total of the chemical and electrical force, and then as a result, the electrochemical force will be also acting in that one direction. Now, as you would imagine, the magnitude would be even larger. If I have a chemical force wanting to move potassium into the cell and an electrical force wanting to move potassium also into the cell, I'm just going to add those two numbers together. The direction is going to be in the same direction that they're both going in. And that's a pretty easy scenario, right? The sum total would be the electrical force acting in that same direction. Now, here's where things get a little bit more tricky. If the chemical force and the electrical force are in opposite directions, what we're going to have to do is determine the direction of the stronger force. So now we're going to have to figure out which of these two forces is actually stronger, which has a bigger magnitude. That will be the overall direction. Now, in order to get the value of that magnitude, we're going to subtract the smaller force or the weaker force from the larger force. And as you can already imagine, that would be a smaller number there, right? That magnitude would be smaller since we have to do some subtracting. We have to subtract the weaker force from the larger force, and then the overall direction would be in that of the stronger force. Okay, now here is somewhat of a teaser question, a challenge question. If a chemical gradient existed, under which conditions would a particle not be transported across the membrane, even if the membrane was permeable to that particle? Okay, so I'm going to give you a minute or two to ponder this, but let me sort of break the question down again one more time. If a chemical gradient existed, so let's say we have a difference in the concentration gradient, under what condition would have to exist for there to be no movement across a membrane, even if the membrane were permeable to that particle? And just sort of a hint here, this is describing what the electrical force would have to look like for there to be no movement of that particle. Okay, I'm going to give you a minute to ponder this one because this one may be a little bit more of a challenge. Let's see. Okay, so one response here, if the electrical force is higher in magnitude. Okay, we're somewhat going along the right lines here, but this is not actually correct. But this is a good guess, good start. So if the electrical force were higher, based upon what we just described, we would simply move the particle in the direction of the electrical force because it's a bigger force, right? In theory, let's see. If electrical force was opposite and equal to the chemical gradient, excellent. Thank you, and perfectly said, right? So the electrical force would have to be equal, but opposite to the chemical force for the particle to move in no direction, right? For there to be no movement of that particle. So the equal but opposite electrical force would simply cancel out the chemical force, and there would be no movement of that particle. All right. And that is actually a phenomenon that we study, and that is called the equilibrium potential. All right. So when the electrical force is equal to but opposite the direction of the chemical force, there's no net movement. In other words, the ECDF, the combined electrochemical driving force, is zero, and so the particle doesn't move. So that, as we described, is called the equilibrium potential. Right? It's the specific membrane potential value when the electrical force is equal to but opposite the chemical force, and so we see zero movement of said particle. If we were to look at a cation like potassium, potassium's equilibrium potential is -94, right? And basically every single particle has their own equilibrium potential. It's the specific value, and it will differ for each ion, right? For potassium, the value is -94 millivolts. What that means, when the membrane potential is at -94 millivolts, the chemical driving force for potassium is out of the cell, and it's the exact same magnitude as the electrical driving force for potassium, which is into the cell. Therefore, potassium is at equilibrium, right? Potassium is not going to move. Its chemical force is exactly canceling out its electrical force, right? So there's zero movement. So the equilibrium potential is really important for us to understand how particles move, because guess what? Particles are usually trying to move to get to equilibrium. They're trying to move according to their force until they arrive at their equilibrium potential, and then there will be no movement. So when the membrane potential is moving, depending on what value the membrane potential is at, different ions can either be moving or they can be not moving. So when the membrane potential gets to -94, potassium stops moving because it is at equilibrium. All right. Hopefully that makes sense, but as we continue on, we're going to keep reiterating this idea. I know this is somewhat of a challenging topic traditionally, so I'm going to kind of go a little bit slower here, but please let me know what questions you have as we go along. So the equilibrium potential is when the membrane potential of that specific ion is balanced out. And so the force is zero, right? The electrochemical driving force, the sum total forces acting on potassium is zero, and potassium doesn't want to move. All right. Okay, let's illustrate how we determine that force here. So let's walk through an algorithm, right, or a flow chart that will help us determine the direction of the electrochemical driving force. So the first thing we want to do is we want to identify the direction of the chemical and electrical driving forces. So let's put that at the top of our algorithm here. So identify the direction of, and I'm going to abbreviate CDF for chemical driving force and EDF for electrical driving force, right? So we want to identify the direction of the electrical and chemical driving forces independently. And then we're going to see two things. There are two scenarios at this point. Either they're in the same direction, which we talked about, it's pretty straightforward, or they're in opposite directions. So let's look at what each of those scenarios would look like. So if the electrical driving force and the chemical driving force are in opposite directions, all right, then we want to compare the equilibrium potential for the ion in question and the membrane potential that it's currently at, right? So now we want to compare the equilibrium potential, which is E subscript X, versus the membrane potential, right? The subscript M. So we're going to compare these two values if the forces are in opposite directions. Now, the thing we want to know here is that the equilibrium potential is a reflection of the concentration gradient, and the membrane potential is a reflection of the electrical driving force, right? So the equilibrium potential, a reflection of the chemical driving force, i.e. the concentration gradient, and the membrane potential is a reflection of the electrical driving force. So therefore, we have three different scenarios here. Okay. The first one is if the equilibrium potential is greater than the membrane potential. All right. So if the equilibrium potential is greater than the membrane potential, then the chemical driving force is greater than the electrical driving force, and the electrochemical driving force will follow the chemical driving force, right? The overall electrochemical driving force, right? Combining those two forces, that direction will follow the chemical driving force. All right. So again, the equilibrium potential here and the chemical driving force will be the greater direction or the overall direction of the particle, the ECDF. All right. The second option here is if they're equal, and that's kind of what we just described. If the equilibrium potential is equal to the membrane potential, then there's no movement, right? Their ECDF is going to be 0, and the particle is said to be at equilibrium, right? The overall ECDF equals 0. In other words, the particle is at equilibrium or no net movement. Okay. So if they are equal, then the ECDF is 0. That's our main point here. The third scenario is the opposite of the first. So if the membrane potential is greater than the equilibrium potential, then now we know that the electrical driving force, or the direction of the electrical driving force, is going to be the greater force, right? And so the particle is going to move in the direction of the electrical driving force. So here we say that the EDF is also greater than the CDF, and the overall ECDF will follow the EDF, right? The electrical driving force. So here we're looking at the membrane potential being the greater force, therefore the electrical driving force, the direction of the electrical driving force is the overall direction of the particle. And then lastly, the most straightforward scenario was if these forces are in the same direction. So if the EDF and CDF are in the same direction, right, then the ECDF simply moves in that general direction, right? The ECDF moves in that direction. And then we add the value of both. Okay. So basically, this is somewhat walking us through the different options that we have if we look at our forces separately: chemical driving force first, the electrical driving force, and then we can have different scenarios depending on which is the stronger force. So we said that if the equilibrium potential is a greater value than the membrane potential, then the chemical driving force is the direction of the particle. If the membrane potential was a greater value than the equilibrium potential, then the electrical driving force was the stronger value. And so in each of these two scenarios here on either side, we're going to want to simply subtract the smaller force, from the larger force, and that would be a smaller value in terms of the overall magnitude. And then lastly is if the forces are in equal but opposite directions, they will cancel each other out. The particle will be at equilibrium and there will be no net movement.